Okay, we are recording. All right, so first, anyone watching can see today's theme, Batman, and NaN, so it's either not a number from numerical analysis or sodium nitrogen from chemistry. However you want to look at
Which
it.
is actually not what it stands for.
What does it
Okay.
stand for?
Nothing.
Not that.
So it's not sodium.
Sodium nitrate
It's
is
not
NaNO.
Yeah, but I said sodium nitrogen.
Which is nothing.
Nothing.
It
Yeah.
doesn't
It's
exist.
not possible.
Yeah.
Maybe you should.
Yeah, maybe.
Oh,
yeah,
oh,
exactly. Come on, nature. What are you doing?
So it's also an indeterminate form.
What is that?
Back to math world, but yeah.
Is that something in numerical?
No, calculus.
Ugh.
Is it
Well, anyway.
0 over 0?
NaN is 0 over 0.
Mhm.
Yeah. So I was thinking if sodium nitrogen does not exist, then
So that's
it's equally undefined. So. Oh,
No,
I had Cal 4 in 2011. So
okay.
I enjoy
I'm
math.
not jealous about that.
Okay. Anyhow. All right. Who's bugging me?
Is your phone on
Okay.
there?
What? No, it's on silent.
Oh.
That was someone else dinging. So. No, actually, that was my computer dinging, wasn't it?
Yeah, it wasn't me.
Okay.
I
Oh,
thought it
oh,
was me, but it wasn't.
Okay. All right. Okay. So the plan is. Was this really like Joker and Catwoman or something?
No, that's Two-Face.
Oh, Two-Face. Okay. Yeah.
Oh man, I take back all of that flaws that I gave you. You just called that. I take it back.
The Joker's got the crazy hair and the.
No, it's
Well, Joker.
No.
I didn't think it was a good Joker. I just totally forgot about Two-Face.
Yeah.
So.
Okay, I guess half applause.
That's just mean. These are independent events. Okay. So, but again, I've made other similarly soul-crushing statements to you before, I guess. Like,
Yeah.
like, oh, I've never read Harry Potter.
Yeah, which is just broke my heart.
Yes,
I read
but
the first three.
I addressed that one.
Bigger and bigger. I just
okay.
ask
White
about
chocolate.
awesome. But then cover of I was this big, and I'm not gonna read 900 pages of Harry Potter.
You
And
should.
I was going
It's
forward.
worth it. It doesn't matter. It's worth it. It's
And
worth it.
Black dies
Well-
in the end in something, and then I was reading the I'm
Well,
not reading
That
it.
was
Now,
in the
now,
book
now that
already.
Haley's been traumatized again, let's do some DE.
Yeah, but
Um,
Black dies. What was the point
You
of
can
Black
read
dies?
one book in like 3 days if you really like.
I
You
read one
can
book in
know.
like 1 day.
Yeah,
Yeah.
yeah. Well, because it's
Show
smaller
off.
books, you can read it.
Yeah, the small, small.
You can
Yeah,
read the
the first
book.
two ones I can read in 1 day.
Yeah.
I did all, like, that's how I read all
I
of
mean,
them.
if you don't need your sleep.
Yeah, you literally can't do anything but read.
I know about
Okay.
I did.
Punch my sister
When I was
in
like
the face
12.
so she wouldn't
I
take
was
the
young,
book
I
away.
couldn't run.
Like,
I was like obsessed.
So that
I think I finished the
one day.
seventh
My
one.
sister was such
in
a
like
big
3
Harry
days.
Potter. She reads,
And it's like-
rereads every
Um,
I regret it. Because
Like,
I
it's-
Seven was big.
I read it.
I think he wants to teach.
I'm
Guys,
sorry.
This time it's them.
I know.
Oh my gosh! Well, what it wasn't me.
So just to recap,
That's the one.
so A is 2 by 2, and the eigenvalues are complex, A plus or minus BI, and then the eigenvectors are complex as well, expressed in terms of real vectors, U plus or minus IW. Okay. Let's see. Also, we're going to assume that the initial data, so x of 0, actually not x, alpha of 0, which is some vector C has coefficients C1, B1 plus C2, B2, and these coefficients, C1 and C2, are also complex. So we write them as C plus or minus DI. Okay, so that's just a recap of notation I started with last time, but we want a real alpha t. So we want to be able to describe the solution in terms of only real entities, never do any complex arithmetic. Okay, so I've done some manipulations, which I won't repeat here, Vernon knows anyway. Where we left off is alpha t is 2e to the at, where a is a real part of the eigenvalues. And then I have cu minus dw cosine bt, where b is the imaginary part of the eigenvalues, minus cw plus du sine bt. Okay. All right. So, but the thing is, the C and D here come from the complex coefficients of your initial data in terms of V1 and V2. So what we also want, and we don't have yet, is, all right, so we, okay, I won't say what we want yet. So let's assume that the initial data is instead of, sorry, I just wanted it to be over.
Me too. So that's right.
Show of hands.
Okay.
Go ahead.
So the initial data, that bad, huh?
I was just trying.
Okay. The thing is that I can no longer tell if Haley's ever being sarcastic or not.
I think she's being for cereal right now.
Super serious.
Okay. Man, what happens this morning? Okay. The initial data is expressed in terms of u and w. So we have constants ku plus hw. So we want to express a solution in terms of k and h instead of c and d, because to get c and d we'd have to do complex arithmetic. We don't want to do that. Okay, so that's where we finally do something new today, after being in class for nearly 15 minutes. Okay, so what we do is we play a matching game, because alpha 0 now has two different representations, c1 v1 plus c2 v2, but that's also equal to ku plus hw. Now this side is entirely real. The other side has real imaginary parts. So we just need to isolate the real imaginary parts. So, so this can be written as c plus di u plus iw plus c minus di u minus iw. And it's still equal to this. Now, this whole expression is supposed to be real, so if I were to break this up into, like, regroup everything to get real imaginary parts, the imaginary part's going to be 0. And then the real part will tell me what k and h is. So, so if I multiply out all of this, what you would get is, okay, I would get 2c times u plus minus 2d w. And this is matched against ku plus hw. So now it tells me what k and h are. So k is equal to 2c, and h is equal to minus 2d. Okay. So, what do I do with this? Now I just need to incorporate that into this solution right here. And notice I have a 2 sitting out front. So any place where I have a 2c, I can replace that with k. Any place where I have a 2d, I can replace that with minus h. So by making these substitutions throughout the solution, I get rid of c and d altogether. So the only entities I'm going to have in the solution are real items, a, b, k, h, u, and w, all real. Okay. Your talent for hurting yourself while doing nothing is utterly amazing.
I was trying to pick my hand up, and I caught it on the table.
No, this is how it's been for like over 4 years. I cannot turn my head for a second. All of a sudden I hear that distinctive, ow!
It's red now.
Some traditions never die. Okay.
I had to take me to the hospital.
I haven't.
I did have a roommate that did the hospital.
This is why I hope you end up in medical school.
Huh?
This is why I hope you end up in medical school.
So you can get yourself.
Oh, I was gonna say that way I'm like just constantly like
Or just
if I
your
get hurt,
outcome
I'm right there.
I'm just kidding.
Hey!
Well, that's a side benefit, but yeah. Okay, so after I make all the substitutions in there, I get the following. Alpha of t is equal to e to the at, and I have ku plus hw cosine plus hu minus kw sine dt. Okay. Now, I explained earlier, last time, how to get the vectors u and w once you have the eigenvalues. Because the thing is, the eigenvalues, you're just using quadratic formula to get those in this case. Well, really in any case, because they always occur in complex conjugate pairs. So quadratic formula will isolate the real and imaginary parts for you. So you have no problem getting A and B. So just to recall, you get u and w from these equations. A minus little ai squared plus b squared identity times u is equal to 0. You can solve that homogeneous equation, and then w is minus 1 over b, a minus little a identity times u. So really, step 1 is getting the eigenvalues. Step 2 is getting these real and imaginary parts of the eigenvectors. You don't bother computing the eigenvectors themselves. There's no need. And then you solve the system. Ku plus hw is equal to c, which is your given initial data, in order to get k and h. So you're solving basically a 2x2 system of equations here. So once you have all your ingredients, A, B, K, U, H, W, then all this information goes in here, and then bam, you have your solution as a function alpha of t. Okay, so I'll make a note here for your notes first. You get A and B from your quadratic formula for the eigenvalues. Okay, so really those are all the steps you need. So starting directly from your matrix, first thing you always do for your matrix, get the eigenvalues. all of this gives you the solution. All right. Okay, so any questions about how to get the solution?
So one in the form of KU plus HW, right? Always.
Yeah. Now, so this sort of 2x2 case. I will talk about a more general n/n case in a little bit, but this is going to naturally generalize to that. So this is the solution of the system x prime is equal to ax, and x of 0 is equal to c. So this often system, if you have a non-homogeneous system with the same matrix, then your solution will have a similar form. It's just going to have this integral involved that comes from the non-homogeneous term. Okay. So in fact, let's see. Easy way to do this. Okay. So in fact, what we could do is we have a way of writing e to the at. So you can write it as uw, and then we have this matrix involving the real and imaginary parts of the exponentials of the eigenvalues. So this is for real part of e to the lambda 1t, and then the make sure I get this right. Yes, the imaginary part of e to the lambda 1t, and then the imaginary part of e to the lambda 2t, and then the real part of e to the lambda 2t. So you have this 2x2 matrix. And then you have the same matrix uw inverse. So it's kind of like when we diagonalize a matrix, you have like P, D, P inverse, but D was a diagonal matrix. That's what you do in the real case. Here it's not a diagonal matrix. Because if we had a diagonal matrix, we'd have complex eigenvalues exponentiated along a diagonal. We'd have complex entries again, and we'd have complex eigenvectors here and here. We want everything to be real. So to make it real, we have this different structure that is, so it's not diagonal, but at least it's real. And actually, I can give you formulas for these. The real imaginary parts of e to the eigenvalue, this is just e to the at cosine bt. This is e to the at sine bt. This is going to be minus e to the at sine bt. And then e to the at cosine bt again. Okay. So at least we have this representation of the matrix exponential in contrast to what we had in the real case, where we had eigenvectors, diagonal matrix of exponentiated eigenvalues, eigenvector matrix inverted. Okay. All right. Now that we have a formula from a solution, we want to be able to get some idea of what the integral curves look like from a solution formula. But actually, to help us understand the integral curves, it's actually a little easier to work with the solution in this form, because we can. This also gives us a solution. All we'd have to do, the only thing I'm missing is if I multiply both sides of this by c, then that's alpha of t again, because that is the solution, which I can also write as the flow from this initial data. Okay, so writing a solution in this form gives us insight into what the integral curve alpha of t is going to look like. We just need to express this in terms, or interpret this in terms of geometric operations. Okay. After all, this is the geometry of the integral curve section. So I guess I should say a little something about that. Now, so if I continue with that formula, so alpha, flow, c. Now, I'm going to start with that previous formula, but I'm going to take the e to the at, because notice that's in every single entry. I'm just going to factor it out. The e to the at. Then we have the matrix of u and w as columns. And then I have this matrix cosine, sine, minus sine, and cosine again. Okay, and then I have uw inverse times c, but this is just a vector of coefficients h and k. Wait, ku plus hw, yeah. Okay. Now, this matrix here, cosine, sine, minus sine, cosine, all the same angle. It's one of those good to know things, and I use that phrase a lot, but it's true, of what a matrix like that does. And this comes up in many contexts. So, what this does, taking this matrix, multiplying by this vector, it rotates the point kh, I don't know why I'm compelled to write h first. Rotates the point kh, so x coordinate, y coordinate, clockwise through the angle theta, which is bt in this case. So anytime you have a matrix, 2 by 2 matrix, cosine, sine, minus sine, cosine, that's a clockwise rotation through, it has to all be the same angle, or it doesn't count. That's a clockwise rotation through theta. If I put the minus up here instead of down here, that's a counterclockwise rotation.
Upward?
Negative sign? Yeah, up here instead of down here. Because that's just the inverse matrix. Because the inverse matrix would do the rotation the other way to bring the point back to where it was. Okay. So this kind of thing comes up more often than you realize. Okay. So, if what we're doing is taking a point kh and we're rotating it through an angle that depends on t. So, in the plane, let's say your point kh is right here. So we're just going to keep rotating. So if the angle is bt, then what behavior are we going to get over time as t increases? Where's this point going to go? Yeah, it's just going to keep going around in a circle. So it'll start here, keep going clockwise in a circle forever. Now, what would the radius of a circle be? What? Not b. Try to hold your hand in front of your mouth.
Root under h squared, no.
Maybe like the sun thing.
Well, okay. Yeah, it's this distance.
Yeah.
The square root of k squared plus h
Yeah.
squared.
So the radius is square root of k squared plus h squared. Okay, so this part of the solution, the only part I've discussed, left to its own devices, it would just go around in a circle. Okay, now, but the thing is that's not the whole solution. There's still these two more pieces that we have to talk about. Because now we take the x and y values that we get from this circular rotation and we multiply the x value by u and the y value by w. So the effect of these vectors is to, so you can think of these as being like they define an ellipse. In the plane. Now, if the vectors u and w had the same, well, if they were like orthogonal and had the same magnitude, then it would still be a circle, because a rotation of a circle is still a circle. And that's,
It's on my computer, but
oh, okay. I thought, oh, somebody dropped a pen or a pencil, but
coffee. So I gotta get rid of
If you wanna get it off the books.
I have a bunch
yeah,
of
dude.
I have a bunch of napkins in my
Did
office.
you use the laptop? No.
No, it's on the laptop. Sorry, guys.
Don't bother me.
I'm not gonna hit Harry.
I've read Harry Potter. I don't deserve
I've read Harry
this.
Potter too.
I have to.
Well, I read half.
That doesn't
Yeah, that
count.
doesn't count.
Three
You
sevens.
get
Doesn't
50%.
count.
And I
Actually,
know,
you get
Three
less.
sevens
I
does
know,
not
I
half.
know black guys. I know Ron and Harry, no, Ron's sister and Harry married. And
No one
Half.
cares what you know.
3 sevens is not half.
Yeah,
I
that's,
thought you were a math major.
yeah, it's 42%. Gee.
or 42%.
That's not half.
That's
Not
40
even, because the class books are so huge that it's more just like, you get like a 12.
and
Yeah,
then,
like-
like two cards.
That's two books.
The two free books, I'd say, yeah.
Yeah.
You failed.
Well, favorite 20% left.
I passed another thing.
I'm gonna get Corbin to fire
I think you need to go a little higher than that.
you. Yeah.
I'll,
Go to Dr. Sherman.
literally set him on fire.
I'll read all of them over father.
Actually, no, that would be funnier.
I'll read all of them over father, I promise.
He promised. Pinky promise.
Isn't this how I got you to read them?
Watching the movie.
I think this is how I got both you
No, I
and
understand.
Dr. Perry to read them.
Watching the movie.
Dr. sitting here. Yeah,
That's
when
a
we
long
did
one.
research, I told him, like, we were talking about Harry Potter, and he was just like, yeah, I never read them and talking about it, and I was like, I'm not gonna do research with you unless you fix this. This is a problem.
You didn't give me that specific threat, but you did tell me that I like crushed your soul or something.
Yeah, you
So I
did.
took pity on you and
No, we traded. I watched Doctor Who.
as a result read 7 books and watched 8 movies.
Yeah.
Okay, that's good. Although, actually, Diana and I watched some Doctor Who last night, and certain ones are just really stupid.
Yeah.
Oh, is it the last Doctor now, or?
Actually, I
It's
haven't
like
watched. I haven't watched any with the current one.
It's cold in here.
It's always cold in here.
I feel colder now, and I'm in like a long sleeve and pants. and whatever this is called, a blanket.
So as an example, let's suppose that the vector w
Yeah, but he has a hood. Like,
points
it's
this
cold.
way, and let's suppose that the vector u points this way, because they're not necessarily perpendicular to each other, and they're going to have different lengths. So they could be any vectors at all, depending on the matrix. So, but these vectors basically define an ellipse, where the point C would be some point on the ellipse. Okay. So now we have to define an addition. So now the part of solution from here onward. So I'm still ignoring the e to the at. So solution is now going to go around this ellipse forever. And in fact, if a equals 0, that's exactly what we would get. But now, the last part of the solution, the e to the at, causes spiraling. Now, what kind of spiraling do you get? So it's inward if a is negative. So it'll spiral in this elliptical pattern towards the origin. So something like this. That's kind of messy, but you get the idea. And spirals outward if a is positive. Okay, so that's how solution curves behave in this 2x2 complex case. Of course, it's very difficult to discuss the geometry of solution curves for n greater than 2. We could try for n equal 3, but heck. All right, so any questions about what are we getting geometrically in this case? And so if you break it down by the one stage at a time in terms of individual operations, rotation, and linear combination to form some sort of ellipse, and then the spiraling factor, then it's easier to understand why the solution behaves the way it does. All right. And as you can see, if you look at your notes from the example I did last time, for the real case, the behavior is extremely different, because before real eigenvectors and eigenvalues, I'd have your eigenvectors being pointing in these directions and solutions approaching one eigenvector or the other, and either going toward or away from the origin, depending on whether the real eigenvalues were positive or negative. So this behavior is completely different.
So they would still be a circle if the magnitude of U and W would be the same, right?
We'll see. You definitely need the magnitude to be the same, and
Yeah, to be orthogonal.
actually, I think magnitude being the same would probably be enough.
Okay.
Yeah. Now, the vectors were a different length, but orthogonal. You'd still have an ellipse, but it'd be like a regular ellipse, where you'd have the x and y axes be like your major and minor axes. And so if they're orthogonal, then u and w basically serve as the major and minor axes of the ellipse.
Right.
And so depending on which one is major and which one is minor depends on which vector is longer. Okay. So now let's step through an example involving a complex case, and then we can generalize from there. So I guess this means I'll start chapter 5 on Monday, which means I have to do notes. Dang it.
Or you have another option.
Yes.
I mean, that could very well be the last class we have in the month of October. Because,
So we have class on Monday, we don't have class the rest of the month.
well, definitely not on the Wednesdays.
Right, the Wednesday because you're gone, and then the next week's the SIAM thing, right?
Right.
I think you were debating on Monday.
I still haven't decided about Monday.
Okay, well, if we have class Monday and you finish, we should just not do that Monday. It's like not do
Oh.
Monday.
I'll look at the schedule. I'm pretty sure we're ahead, and I don't need to get further ahead, but we'll see. Okay. All right. For example, we'll solve this initial value problem. Generic one, but here's our matrix. 2, 3, minus 3, 2. Now, if you have a matrix like this that is symmetric except for a minus down here, and but also the same elements on the diagonal, I'll still work it out so you can see it, but it turns out the eigenvalues always turn out to be the diagonal entry is the real part, and then the off-diagonal entries are the imaginary parts. So if you have a matrix that looks like that, you just know. But now I'll prove it to you. So the determinant A minus lambda identity. Okay, so we get 2 minus lambda, 2 minus lambda, minus 3, and 3. So we get 2 minus lambda, I'll write lambda minus 2 squared. It doesn't matter what sign I make it. Plus 3 squared. And we want this to be equal to 0 to get the eigenvalues. And so what that would mean is lambda minus 2 squared is equal to minus 3 squared. So it means that lambda minus 2 is equal to plus or minus 3i. That's how you can see that those are the eigenvalues. Okay. So, and thank your K-12 teachers who said you could not take a square root of a negative number. I showed them. Okay.
We did imagine numbers when I was in like 10th grade.
Oh, okay.
Yeah, we can.
I probably saw them sometime in high school, but I don't remember. Well, it was the mid '80s. Was I thinking of those things like Chuck Norris facts, like Chuck Norris can divide by 0, something like that.
Are we gonna have to replace her with Dr. Lambert instead of Chuck Norris? Dr. Lambert's kicked butt.
No, it's roundhouse kicked. You know, yeah, X. Like, answer anything, Chuck Norris can roundhouse kick that. So it's
Actually, when they got his own reaction in Chuck Norris facts, he's fine with him and all that, but his response to it was like one of the lamest things I've ever heard. I'll have to look it up.
I think that's why they do that, is because he's actually kind of lame. Yeah.
Yeah, he is. So, okay. So now we have the eigenvalues, 2 plus or minus 3i. So we're not going to compute the eigenvectors because we don't need them. So to get vectors u and w, we solve these equations. So a minus real part times identity squared plus the imaginary part squared times identity times u is equal to 0. So we solve that first, and then we have the other equation. W is minus 1/3, because 3 is b, times a minus 2 times identity times u, whatever that is. Okay, so now we'll just form this matrix and solve a homogeneous system with u being equal 0. Okay, so a minus twice identity. So I subtract 2 from the diagonals. So that's just going to be 0, 3, minus 3, 0. And now I need to square that. Okay, so 0, 3, minus 3, 0. Good old matrix multiplication. So, okay, so I get, wait a minute, that's weird. Minus 9? Oh, okay, yeah. 0, 0, 0, 0, and then minus 9 plus 0, so minus 9. Okay. So I get that. So then I look at a minus 2i squared plus 9 times the identity, so I've thrown this extra term. So that's going to be minus 9, 0, 0, minus 9, plus 9 times the identity. So what am I going to get? Yeah, it's all 0. I'm like, okay, now what? That seems kind of odd. So I'm trying to solve the equation 0 matrix times u is equal to the 0 vector. Well, it doesn't matter what u is. Okay, actually, I'll go ahead and go to the other board. You everything cleaned up?
Yeah.
Okay.
Pretty much.
All right. So to solve this strange equation, 0 times u is equal to 0, well, u can be anything. Although u does have to be non-zero. We need to have non-zero eigenvectors. So we could just choose. So I'll let U be equal to vector 1, 0. So now I need W. So W is minus 1/3 A minus 2I times the vector 1, 0. So, well, A minus 2I, I computed out earlier. That's 0, 3, minus 3, 0 times 1, 0. Now, when you multiply a matrix by 1, 0, all that does is take the first column. So it's minus 1/3, 0 minus 3. So then you simplify that and you get 0, 1. Okay. Okay. So now that we have that, okay, we can write down the solution. So alpha t is e to the 2t, because 2 is a real part. And then we have u and w, but unfortunately that's just the identity matrix. And then we have a rotation matrix, cosine 3t, sine 3t, minus sine 3t, cosine 3t. And then we have our kh, but kh is equal to the matrix uw inverse times c, your initial data. But the thing is, the matrix uw is identity. So this is just going to be, it's just going to be c. Okay. So in fact, these are just the components of your initial data. So I'll simplify this. So that's e to the 2t times, I'll abbreviate this as a rotation matrix with angle 3t times c. So what happens is the initial data gets rotated around a circle where a radius is the magnitude of c, but then we have this e to the 2t, and what does that cause?
Spiraling out.
Out, yeah, because the eigenvalue is positive. So what happens is wherever c starts off at, that's going to spiral, it's going to go clockwise and spiral out like that. Okay.
So the 3t is the angle.
Yes.
So how do you show that link, the magnitude of the angle link?
Can't really show on the plot unless you do like a time lapse. So it affects the speed at which the spiraling happens, or really just a rotation around whatever curve you're getting. Okay. Something is off here. Am I missing a page? Okay. Yes, I'm missing a page. Let me see if I have it here real quick.
There's no trash can in here.
No.
Alrighty. I'm just looking at that.
Okay, go.
Yeah, they just, yeah. I couldn't hear you, so.
Huh?
I couldn't hear you.
Oh, I haven't, okay, I mean, needed,
Yeah, this is pretty good.
yeah, this notebook and there too.
Nope, not there. Oh, page 10. Okay, there's very little on page 10, so we'll hold on to this until I get to that point, because I still need to do page 9. Okay, so any questions about this solution, or how we got it? Okay, so eigenvectors get these u and w, and then bam, you can write down the solution. Normally it would be a linear system to solve, in this case it was a trivial one. Okay. Alright, doing pretty good on time.
It's not always gonna be identity, right? It's not always gonna.
No, definitely not.
So, and, yeah,
Yeah, so we missed the stage in which the circle is deformed into an ellipse, but that didn't happen here. Okay.
but it's going to the homework problems, right?
What?
It's going to conform to the homework problems.
No. No. I picked out a couple problems from this section dealing with these 2x2 systems, and in both cases, the eigenvalues turn out to be real. So, okay. So what I did last time was if you had all real eigenvalues and it's diagonalizable, and then what happened if you have a 2x2 complex case. Now we need to get a little more general than that. But not completely general. So we'll still assume that A is diagonalizable. What?
Is it actually that word?
It's
hard to say.
Diagonalizable.
Yeah.
It's too long.
Well, you know who else hates it? Every spell checker ever invented.
Yeah. See, I'm not crazy.
Diagonalizable. Of course, you can always avoid it by saying it has n linearly independent eigenvectors. So let n be equal to q plus 2p. I know that none of you will believe me, but when I was in elementary school, I had perfect penmanship.
You had perfect what?
Penmanship. Like cursive and everything.
I think mine's got worse since I was.
Do we have different definitions of perfect?
No, it was by any measure. All my teachers, yeah. So, but at some point I just stopped caring. About writing with my right hand like a lefty would write doesn't help matters. But it's good for jokes sometimes because I'll be writing and someone will say, "Are you left-handed?" I'm like, well, no. Okay, so Q is a number of real eigenvalues let's see, do I have notation for this? Lambda 1, lambda 2, up to lambda q. And then P is a number of complex conjugates pairs of complex eigenvalues. That's why we have n equals q plus 2p. Okay. So the complex eigenvalues, write those as aj plus I bj, so plus or minus, and then j equals 1 to up to p. Okay. And then we have eigenvectors to go with these real and complex eigenvalues. So v1, v2, up to vq, so these are the real ones. And then we have uj plus or minus I wj for the complex case. and that's j equals 1 to up to p. So similar notation as I have been using. Now in the complex case, I just have to put indices and everything. Okay, and then we'll assume that the initial data, so we have x of 0 equals c, which is some vector in Rn, and c can be represented as a linear combination of all these real eigenvectors and the parts, real imaginary parts of the complex eigenvectors. So we have this expansion. Okay, so mj, vj, so this contribution comes from the real eigenvectors plus some of, so same notation, kj, uj plus hj, wj. Okay. So all these vectors, the real eigenvectors and the parts of the complex eigenvectors, they all form a basis for Rn. They're all linearly independent. So any vector in Rn can be expressed as a linear combination of them, and these m's, k's, and h's, those are the coefficients that we get. So what you could do, you could think of it this way as a linear system. You form a matrix from the real eigenvectors, and then the u's, and then the w's. I'm going to run out of room, aren't I? Okay, well maybe not. And then my coefficients are the m's, there are q of those, the k's, and the h's. So these are all the coefficients stored in one vector. That's equal to c. So that is the system of linear equations that you'd have to solve. So once you have all the eigenvectors or eigenvector parts, you can just form a matrix from them and set the right-hand side equal to initial data, solve, and then you have all your coefficients. So that's what it takes to solve this system.
So V's are the real.
Yes.
And U's are the real part of the complex guy.
Yeah.
And the W's are the complex guy.
Yeah, they're the imaginary parts of the complex eigenvectors, the w's.
Yes.
Yeah, from that.
Right.
Okay. So once we're able to get all this stuff, so now the thing is, we would get all the eigenvalues and eigenvectors in the exact same way as we did in the previous examples. So you can take a characteristic polynomial, try to get roots. So the real roots would be your real eigenvalues. And then when you see that you have these complex conjugate pairs, you would solve for the u's and the w's in the same way as I did in the previous example. You'd just be solving p of those systems, but you form them the same way. Nothing's changed there. Okay, so once you have all of this, now you can express a solution in a similar manner as in the special cases I did before. You're just putting everything together.
From that vector right there, you've got from V1 to VQ, and you have U1 to UP, and W1 to WP.
Yeah.
Is it supposed to be V1 to VP?
No.
It's
Q, because there are Q real eigenvalues,
okay.
and P pairs of complex ones. Okay. All right. So then, the solution. Let's use flow notation, but it's also alpha t if you like. Okay, so we have a sum. So first, from a real case, these coefficients, e to the eigenvalue times the real eigenvector. So that's a real contribution. And then the sum for a complex part. So e to the real part times t. So that does the spiraling in or out, depending on whether each individual aj is positive or negative. So you could have spiraling out in some terms and spiraling in others. You just never know. And then you have, you take a linear combination Okay, using W. So so you have this ellipse making in each plane, and then you have a rotation to the angle B sub j times t, and then you have your coefficients. Okay. And if you were to write out what all of this is in terms of sines and cosines, so that would be KU plus HW cosine BT plus HU minus KW with all appropriate subscripts sine BJT. But that's just carrying out all the matrix multiplication here. But the geometric understanding comes more easily from this form. So what you have is, if you think of all these pairs of parts of eigenvector parts, each one of them forms basically a plane in n-dimensional space. So all these effects you have, this rotation around a circle, deformed into an ellipse, spiraling in and out, is happening within p individual planes that are independent from one another, but then all the effects are added together. So that'd be really hard to visualize.
Does the dimension of P have to be less than or equal to N?
Oh yeah, just because n is equal to q plus 2p.
Oh, okay, yeah, okay,
Yeah.
of course.
Yeah. Alright. Okay. Alright, so that's the most general solution formula I can give for this covers all the diagonalizable cases. So everything except for case of defective eigenvalues. That's the only thing I've left out. So any questions about this solution? It just builds on the other ones. Alright. So I have one last example of for a non-diagonalizable case where you have a non-trivial Jordan block, and that creates a whole other effect. Okay. All right. So I'll just cover this using an example. Most easily done there. Plus, okay. So here's a typical example of a non-diagonalizable matrix. Actually, that would pass for a 2x2 Jordan block, where you have your eigendiagonal, a 1 above, 0 below. Okay. Now, so the eigenvalues so lambda 1 and lambda 2 are both equal to 2, so it's repeated. And then, so the eigenvector, you only have one of them. So you solve A minus 2 identity V1 is equal to 0 to get the eigenvector. But A minus twice the identity is just going to be this matrix. Everything's gone except for this 1 up in the upper right corner. Equals 0. So then if you write out what the solution, or what this system is, equation by equation, all you get is V21 is equal to 0. That's the only constraint. And the eigenvector has to be a non-zero vector. So you can set your second component has to be 0. Your first component can be anything non-zero. So we'll just make it 1. So that is your eigenvector, the only one you have. Oh, boy. I completely got that wrong in the notes. I wrote 0, 1, should be 1, 0. Okay. Now, you need a generalized eigenvector to complete the space. So that satisfies A minus twice the identity V2 is equal to V1. So now you're solving a non-homogeneous system. That's a whole lot easier. So we get 0, 1, 0, 0, V1, 2, V2, 2 is 1, 0. So then you write out what this system is, and you get V2, 2 is equal to 1, and then the other system is just 0 equals 0. So what do you do? So what that means is V2, you set your second component equal to 1, and then the first component can be anything at all. It doesn't matter. It's still going to satisfy it. Again, keep it simple. Let's make it 0. Okay, so those are eigenvectors and generalized eigenvectors. Okay. So now, what form does the solution have? Well, e to the at is normally, well, a is equal to xj x inverse. So that'd be x e to the jt x inverse. But in this case, x is equal to the identity. So x is equal to v1, v2. That's identity. So now in this case, it's just e to the jt. So we have to take that matrix A. So this equals its own Jordan form, and take the exponential of that. And that was worked out in a previous example. So in this case, e to the at is just going to be e to the 2t, t e to the 2t, 0, e to the 2t. So the non-diagonalizability of the system leads to this t e to the 2t creeping up. Okay, so now I just need to multiply this by the initial data. Okay, so now I need page 10. Thank you. Okay. All right, so I'll describe what happens in general terms, or as general as I can for this 2 by 2 case. And then we'll specialize it to this example. Oh, that could have been horrible. One friend who left her laptop on the top of her roof of her car and forgot about it and started going. And
Did it fall?
actually it survived. That's quite amazing.
Wow.
It's safe there.
No, it flew off a car, but it still survived.
Must have not been made by Apple.
Actually, it was.
Really?
And my wife put her iPhone on top of the car and drove from Walmart back to William Carey, and it was still there.
Wow.
That's really funny.
Very
I
disciplined driving. Very
someone
popular.
at high school who did that with their phones. One of those Blackberries. Remember they made those like rubber cases for them?
Yeah.
The only reason it stayed in our car because that rubber
It was
case
stuck.
kept it like stuck to the car.
Okay, so what we have is, in general, B1, B2, e to the jt, B1, B2 inverse times c. And this Jordan form is going to be, okay, yeah, e to 2t, t e to 2t, 0, e to 2t. And this vector, I'll just call it D. Okay. So I want to express the solution as a linear combination of V1 and V2. So if I carry out the multiplication, Okay, so I have e to the 2t d1 plus t d2, the first component. Second component, let's have e to the 2t d2. So now I carry out this matrix vector multiplication, and I get, okay, well e to the 2t factors out of everything, and you get d1 plus d2t v1 plus d2 v2, and now I can specialize to this. So this is a general case where instead of 2, I might have a different eigenvalue, but in this example it's 2. And then in this specific case, this example, because v1 and v2 are the columns of identity, so it's just the vector e to the 2t times d1 plus d2t, and then d2. So that's your point in space as a function of t. Okay. Now, what is the geometry of this solution? We want to see what happens as t goes to infinity. Well, first, the magnitude is controlled by this factor sitting out here, the e to the lambda t. So the magnitude goes to 0 if the eigenvalue is, actually it should say for real, well, yeah. For real part of the eigenvalue is positive, no, negative. And then to infinity, if it's positive. And if it's equal to 0, then the magnitude only comes from whatever's going on in here. But otherwise, the exponential part's going to dominate one way or another. Now, what about the direction? That's the part that I think is more interesting. So what happens here is, if you look at these components, here's the component direction of v1, component direction of v2. But as t is increasing, this part is going to dominate. So, so what ends up happening is the direction is going to be equal to, it's going to approach that of v1 if the coefficient d2 is positive, and then minus v1 if d2 is negative. So it's going to approach, so the directional solution is going to approach v1 eigenvector, and then the part in the direction of a generalized eigenvector is going to be relatively negligible. Okay. So we have these two independent effects going on here. So it's either going towards the origin or off to infinity, depending on the eigenvalue you get. But then what we'll see is this component is becoming so much larger compared to this one, it's staying the same. So, so this component would become essentially 0 compared to this. So that's why the direction is being oriented towards v1. Okay. Especially these lower dimensional cases, we can get an idea of geometric behavior just by seeing, okay, what's the behavior as t increases? What becomes dominant? What becomes negligible?
So is v1 going to be the x direction?
In this example, yes. Yeah, so yeah, it's going to approach the x-axis. Okay. Oh, it's 4:45. I meant to have time for homework questions, or is the homework going well? Oh. Well, of course, at the same time, whenever I open up time in class for questions, you guys never ask anything. Okay, so that means you guys are going to bug me in my office all night.
Yes.
Argue. Okay, well, I'm used to that too. And I'm one of the few who leaves their office door open all the time. So. Okay. Well, at least my day's over. Sorry.
I don't know.
Clearly, I didn't know there was one.
Just kidding.
So, it's not there, never mind.
Oh, I guess I can start recording now.